Okay, organic chemistry 2330. We're going to go with our third and final installment of chapter 15, enolate ions. We're going to continue the chemistry we can do with them with a couple other reactions, okay? The first one is what we call the Michael reaction. And in the Michael reaction, we take a enolate ion and we attack an unsaturated carbonyl compound. What this means is that instead of adding to the carbonyl, we're going to use the fact that that double bond is adjacent to a carbonyl to attack at that beta carbon. So we're going to do a beta carbon addition to this system. And therefore, instead of attacking that carbonyl, we're going to add one over. So we're going to use that to our advantage to make very large chains very quickly. Okay, so in these examples here, what we have is, in this case, we have a diacid ester here, and we have our alpha hydrogens here. Because it's between those two carbonyl compounds, it's very acidic. We form our enolate here, and then it does an addition here, and our final proton ends up on this alpha carbon here when we quench the reaction. Okay, notice here we have a beta keto ester instead of the diester compound here. But because we have two carbonyls right here, we're again going to form the enolate in that carbon in between those two carbonyls. That's going to do the attack at that beta carbon, and we end up with protonation in our alpha site to give us our extended product here. So adding an enolate to a beta carbon that is unsaturated is the Michael reaction, okay? So let's see why this works, okay? So we would expect that our enolate would attack the partially positive carbon atom on the, but in the case of having this double bond in conjugation with this carbonyl here, we can actually form a resonance structure where these electrons will kick up and sit on the oxygen. Our electrons from our double bond will kick over, and we can form this enol form right here. When it forms that enol form, our positive charge is on the beta carbon. Okay, so you'd think that the carbonyl carbon was where all the positive charge lies, but when that double bond is in conjugation with the carbonyl, we have a chance of alkylating at this carbon with the oxygen on it, or the carbon at the beta position. And in the Michael reaction, it always adds at the beta position. Okay, so let's think about how to get this to be very effective, okay? So the first thing we need to have it be very effective is we need to have a double bond in conjugation with an aldehyde, a ketone, or ester, okay? So that's the first substrate, okay? Now, the aldehyde, ketone, or ester we start with is in the final product. We're only going to consume the double bond in conjugation with that carbonyl compound. So this double bond is the one that is going to be added across when we do the reaction. The second thing we need for an effective Michael addition is we need to have a beta dicarbonyl compound or an amine. Okay, so when we have a beta dicarbonyl compound, we can have a diketone, a keto ester, or a diester compound. As long as it has two carbonyls that are alpha, or that has a beta to each other, that means the hydrogen in that alpha position is very acidic and easy to remove. Now, in the case of the amines, we'll show you where the lone pair on the amine acts as the nucleophile and attacks the beta carbon of the unsaturated aldehyde, ketone, or ester to do a Michael addition product. Okay, so what's the first step in this Michael reaction? The first step is we have to create a nucleophile. And we do that by having a base pull off the most acidic proton in the system. In the case of the amines, it's typically that. In the case of the beta dicarbonyl compound, it's always that alpha hydrogen in between those two carbonyls. Okay, so once we form that nucleophile then can come in and attack at that beta carbon, kicking the electrons over to in between the carbonyl and that alpha carbon. and then kicking up the electrons to form our enolate form of our material. Notice this is stabilized such that that anion is stabilized in between the oxygen and that alpha carbon, and therefore it'll sit around until it gets protonated. Okay, so the last step of the reaction is that we end up having either the carbon here or this oxygen deprotonate something that's acidic to create our enol form right here. And then of course our enol form is not the most stable form, and it reverts back to its keto form, giving us our final product. Okay, so we're doing three things here. We're taking a conjugated system, we are taking an enolate, and we're taking an enol-ketol form, and we're adding them all together to generate all the different steps in the Michael reaction. Okay. So let's do a couple examples of this to kind of show you every step of the situation and where things go. Okay. So in this case right here, we have our dicarbonyl compound right here. We have an ester on this side and we have a ketone on this side, but that makes these the most acidic alpha hydrogens here. Okay. Then the next component of our Michael addition is our conjugated double bond with our ketone compound right here. That means that when we deprotonate at this site here, our enolate is going to come and attack here, kicking out this, and then we have our enol-keto tautomerism. And when we do that, we get our final product of the Michael addition is this diketone with a carboxylic acid ester pendant to it. Now remember, in that first video we saw about the enolate ions, that if you have a carboxylic acid in a beta position, you can undergo a decarbonylation reaction if you can form that six-membered ring. And in this case right here, we're going to use acid to hydrolyze off our carboxylic acid ester to give us our bare carboxylic acid. This can now form a five-membered ring with this carbonyl compound. Therefore, we can lose CO2 and generate our diketone compound. So this is one of the really cool things about using this material here. We can generate extended long chains of dicarbonyl compounds. And in this particular reaction, we actually used that acid catalyzed decarbonylation reaction to create a very simple, very symmetrical diketone compound. Okay, so I said before that as long as you can deprotonate something to give you a nucleophile, we can do this addition reaction across an unsaturated aldehyde or ketone. In this case here, we're using a secondary amine as our nucleophile. We can deprotonate here or use the lone pair here to come in and act as the nucleophile to generate our intermediate enolate ion, which then gets protonated in the system. Okay. Now, if we have a secondary amine, we can only do one single addition on that system. Okay. But if we have a primary amine, once we do one addition to give you the once we do one addition to give us this here, we still have an acidic hydrogen on that nitrogen, and therefore it can actually take this one off too. And so the first one gives us our first substitution, or our first addition product, and then our second hydrogen can give our second substitution product. So by choosing your primary or secondary amine when you start, you can get to that just monofunctionalized or the difunctionalized amine at the end of the reaction. Okay, and that is the end of chapter 15.